Now, I would like to start the session. Thank you for coming. Hello, my name is Haruki Okada. I'm a senior software engineer at Line, and I'm responsible for development and operation of Apache Kafka, which is used widely by Line. As you might know, Apache Kafka is a distributed streaming middleware, which is very often used in Line. It is highly scalable, and it has ACL and quota features. Multi-tenant operation is possible. I will explain about Kafka simply. One Kafka cluster consists of multiple servers called broker. And we call message sending client as a producer, and messages receiving and processing a client as consumer. We use a multi-tenant model in which one Kafka cluster is shared by multi-servers. Line official account, Line ads. These are users of Kafka cluster that we are providing. Each service has many producer servers, consumer servers, and our cluster is handling message transfers for those. And currently, there are more than 100 services that are using our cluster. Number of messages is 15 million per second at peak time. Total traffic is 1.4 petabyte per day. It is world-leading scale. In order to maintain the service level of large-scale cluster, we measure the performance, optimize it, and do the troubleshooting on an everyday basis. If you are interested in what we did and the troubleshooting cases, please look at our presentation in Line Developer Day in 2019. Today, I will talk about a problem which occurred in our cluster. I will explain what happened then, what kind of investigation we did, and finally, how did we solve the problem? One day, we were doing the rolling restart of Kafka broker to roll out configuration change. A service developer reported to us, message produce is failing at Kafka. Is there any problem happening? By looking at the logs, we found that the request is timeout at producer. Message was not sent to Kafka during a set timeout period. Unsent data will be lost, so this is a very critical problem. We soon started the investigation. We suspected the increase of the response time of a broker to produce request, because this could happen when replication is delayed, but the broker showed quite normal metrics. Next, we thought produce requests are kept rejected for some reason. Multiple replicas are dead, but we could not find the logs other than request timeout on producer side. During investigation, we found a very strange thing. Response time on broker side was quite normal, but latency on producer side was greater than 16 seconds, quite an abnormal number. When we have this level of bad latency, of course, that request timeout could happen. Also, we found this abnormal latency happens only when we did produce to specific broker. And the degradation of latency started to happen right after we restarted a specific broker. In summary, right after we restarted the broker, produce request latency started to deteriorate. But broker side metric of the response time stayed quite normal. At this point, root cause was not clear, but it was urgent to solve the data lost problem. We wanted to spend enough time to investigate, but we restarted broker once again. Then this phenomena disappeared. So it was settled down, but we need to find the root cause to stop the recurrence of the problem. We need to know why there was a matrix gap between producer and the broker. We need to understand that. We checked the Kafka code and found out that this could happen when it takes a long time to send the request. So as you can see here, let's think how request process time is measured. Request is made on producer side and sent it to broker. It's processed and receive a response from broker completely, and this is counted as latency. And the broker starts response time measurement when it receives the request completely. So when sending request is delayed, for some reasons, it does not appear in broker metrics. So what is the reason for this delay? We assumed that stack of sender thread, which does non-blocking I/O, with some reasons. And to verify this assumption, it is essential to get the detailed information on client side, such as a debug log or profile of async profiler. So with the help of a service developer, we decided to reproduce this problem. So we prepared to get the profile and then started the monitoring so that we can react quickly when problem occurs. And I tried to restart the broker again and again. But the problem was not reproduced after restarting the broker, so our experiment failed. So we don't know enough material, we don't have enough materials, and it is hard to reproduce the problem, so it is very difficult to see if producer was stuck or not. And we made another assumption for why request sending delay occurred. Network performance was degraded in producer and broker route. We made that assumption. So we measured the latency by pin, but it was quite normal. No increase of TCP retransmission, no saturation of the bandwidth, no phenomena that could cause network level delay. So we were struggling in our investigation. Then the problem occurred at different service and different broker. Exactly the same problem happened. The same problem as before, and right after restart the broker, request gets delay in producer, but the broker performance, the response time metric was quite normal. And it was fixed by restarting the broker. Since the problem happened several times, so we tried to see if there are any patterns which are related to request transmission delay. When we checked many metrics carefully, we found that at the restart of broker, node exporter's SYN cookie sent metric had a spike only when the problem occurred. SYN cookie sent metrics increase? What does it mean? I would like to talk TCP SYN cookies to explain this. TCP SYN cookie. This is a mechanism to deal with the SYN flood attack. So let's review TCP's three-way handshake quickly. At TCP, client send the SYN packet to server, and server will add that to SYN queue, then send back SYN+ACK packet. And finally, after receiving ACK from client, server will take out entry from SYN queue and establish the connection and complete the handshake. In SYN flood attack, a malicious client sends a large volume of SYN packet to the server, and it does not send ACK, which is the final step of handshake, and it should send back to the client, but it ignored SYN+ACK from server. So server keeps incomplete SYN forever, and the SYN queue will be full. And it cannot accept the connection from normal server. So this is kind of the DOS attack. Even in flood situation with the TCP SYN cookies, server can accept the connection from the client. Here, we assume there is a Linux kernel. Instead of storing SYN packet in SYN queue, it encodes SYN information to initial sequence number and embed it to SYN+ACK packet and do reply and forget. And when ACK comes back, it decodes the sequence number and take out SYN information by decoding and establish connection to complete the handshake. SYN cookie sent metrics spike. SYN is received, but the SYN queue was full, so it sent SYN cookies and conducted the handshake with a different method. So SYN cookies sent metrics shows a number of that handshake. SYN cookie sent matrix had a spike, which means a broker was in SYN flood situation. Why SYN flood happened? Our cluster broker, including problem broker, gets connected to many producers and the consumers. So when broker gets restarted, what will happen? Client connection will fail over to another broker. When broker comes back, client try to reconnect to the former broker all at once. This caused attack-like situation and the broker became SYN flood situation. Since the problem broker had more than 18,000 connections, so it could happen. That is understandable. So broker was in SYN flood situation. A part of client's handshake was falling back to SYN cookie flow. So we know in some cases SYN cookies causes a degradation of TCP throughput. So let's review the concept of TCP window. TCP window is a volume control mechanism. How much data can be received? Now, it advertises this information on packet to sending side, so sending side will adjust the data volume. Sending side can send packets up to the advertised window size without awaiting ACK from receiving side.
Since the TCP specification stipulates that the window size should be 16 bits, 65,535 is a maximum value. In other words, assuming that the server is receiving side, the maximum amount of data that can be sent at once without waiting for an ACK from the server is 65,535 bytes max. Having an ACK from the server at least every 65,535 bytes can be bottleneck for connections with large round-trip times such as the Internet. Window scaling is a mechanism used to increase the window size beyond 65,535 to improve the throughput. With window scaling, a window scaling factor is advertised to the peer along with SYN and SYN+ACK during the TCP handshake. Then, the actual window size when sending receiving data is calculated by multiplying the 16-bit window size in the packet by the window scaling factor. In fact, 2 to the power of window scaling factor to be exact. This makes it possible to increase the window size beyond 65,535, which increases the amount of data that can be sent at once without waiting for ACK and improves throughput. Let's look at an example. Suppose that the server advertises a window scaling factor of 1 to the client in advance. Now, the server wants to advertise window size equals 102,400 to the client. This is beyond 65,535, so we cannot simply put it in the packet. However, since the window scaling factor is already set to 1, the server will divide the window size to be advertised by 2 to the first and divided by 2 and add 51,200. On the client side, the original 102,400 is restored by multiplying it by 2 to the first. In this way, it is possible to advertise a window size of 102,400, which is greater than 65,535. Now that we've reviewed window size and window scaling, let's get back to why throughput drops with SYN cookies. Instead of storing SYN packets in the SYN queue, SYN cookies were designed to encode the SYN information into a TCP sequence number and embed it into SYN+ACK. However, since the sequence number is only 32 bits, there's no place to embed the window scaling factor because it is limited. This means that window scaling cannot be used when handshake is performed with SYN cookies. As a result, the window size becomes smaller than it would have been if window scaling had been available, which meant that less data can be sent at once without waiting for ACK, and the throughput becomes worse. So, is this the cause of the delay in producer requests? Actually, it is too early to conclude. TCP throughput degradation in SYN cookies is caused by the fact that window scaling cannot be used because there is no space to embed the window scaling factor. In fact, the Linux kernel has a mechanism to embed a window scaling factor using extra timestamp field if TCP timestamp is enabled. And in our environment, TCP timestamp is enabled by default. So it was unlikely that the throughput degradation we saw earlier was occurring. Even if the window scaling factor is disabled, I wondered if it could cause such a sudden delay in requests. The reason is that window scaling is a mechanism to increase the window size beyond 65,535. This is effective in networks with a round trip time such as Internet, but in our environment with very small latency connections, even if window scaling is disabled and the maximum window size is 65,535, we can still get sufficient throughput. Therefore, we decided to experiment with SYN cookies to see what the actual impact of disabling window scaling would be. In this experiment, we set the net IPv4 TCP SYN cookies Linux kernel parameters to 2 to force all connections to be established using SYN cookies, regardless of whether a SYN flood was occurring or not. And then we restarted the broker and tried to reproduce the result. As a result, unexpectedly, the problem reappeared at the stage before disabling the TCP timestamp, that is, when window scaling was supposed to be enabled. Just like in the production environment, the request latency on the producer side was extremely high at 500 millisec, but the response time on the broker side was quite normal. When we took a TCP dump, we found out that the producer was waiting for an ACK from the broker every time it sent a packet, which was a surprise. This is probably because the broker's window size is too small for the producer to send out subsequent packets until it receives an ACK from the broker. The window size on the broker side is 789 as shown in the TCP dump. The actual window size is the result of multiplying this by 2 to the power of window scaling. Checking the SYN+ACK packet with TCP dump, we found that the window scaling factor advertised by broker is 1. This means that the window size was actually very small, 789 by 2 or 1578, which was very small. So the next step was to find out why the window size was such a small value. The tool we used here is called SS, which is a tool for examining the state of sockets. With SS tool, you can specify the -i option to see detailed information about TCP, such as the window scaling factor, congestion window size, and whether TCP timestamp is enabled or not. When I ran SS on the broker where the problem was occurring and checked the socket status, I found something strange again. The SS output window scaling factor on the broker side is 7. However, as shown in the TCP dump area, SYN+ACK should have advertised to the producer that the window scaling factor was 1. As we saw in the previous example of calculating window scaling, if the window scaling factor held by the client server, in this case the producer and broker, did not match, the original window size could not be recovered correctly from the window size advertised by the broker, so they must match. Next, I decided to check whether 1 or 7 is actually used to calculate the window size to be advertised by the broker. Checking the source code of the Linux kernel, we found that the window size calculation is done by function TCP select window kernel function. Since the window scaling factor is included in sock structure of this function, we thought how we could dump it by hooking it. Now, how can we hook such a kernel function? This can be done very easily by using Linux mechanism called BPF. Using BPF, what is BPF, by the way? We can execute user-created programs inside the kernel. BPF is event-driven, and various events can be used to trigger the execution of BPF programs, and kprobe can be used to hook into kernel functions. In addition, there is a toolkit called BPF Compiler Collection or BCC toolkit, which makes it easy to write BPF programs using the C language. Using this BCC, I wrote a simple script to hook the TCP select window function and verified it. It turns out that the broker actually calculated the window size using 7 instead of 1 sent to the producer via SYN+ACK. So why is there such a discrepancy between the window scaling factor advertised by broker to the producer via SYN+ACK and the window scaling factor used by the broker after the connection is actually established? I checked the kernel source code again and found that the logic for determining the window scaling factor is located at the point that generates the SYN+ACK packet to be sent to the client and at the point that decodes the SYN cookies included in the ACKs sent back from the client after sending the SYN cookies were different. In conclusion, this was a bug that existed before Linux kernel version 5.10, which calculated the window scaling factor to be different. Now, all the mysteries are solved. Let's look back. First of all, restarting the broker caused a lot of clients to reconnect at once, and the broker went into a SYN-flat state. Unfortunately, this caused the TCP handshake of one of the producers to fall back via SYN cookies. Then, Due to a kernel bug, there was a discrepancy between the Windows scaling factor advertised by the broker to the producer via SYN+ACK and Windows scaling factor used by the broker when it finally established a connection. And because of this discrepancy, the producer was not able to recover the window size advertised by the broker correctly, and it became very small. What it means is that when the broker advertises a window size to the producer, it assumes that the window scaling factor equals 7, so it divides it by 2 to the 7th, assuming that 2 to the 7th is multiplied. On the broker side, on the other hand, the producer assumes that the window scaling factor is 1, so it tries to restore the window size by multiplying by 2 to the 1st. As a result, the window size calculated on the producer side is very small, 1/64 of the original value, which is very small. Due to this too small window size, the producer had to wait for an ACK from the broker every time he sends a packet. As a result, it took a very long time to send a producer request, resulting in timeout of the produce request, which was the whole story of this incident. Now that we knew the root cause, we had to figure out how to fix it. The first thing we did was to disable TCP SYN cookies in the first place. There was no attack on a broker, of course, but rather a large number of clients that were restarting the broker looked as if it was an attack. But in fact, it caused a SYN flat. All connections were from legitimate clients. Disabling SYN cookies will cause a client to drop SYN while the SYN flat is occurring. But this is not a major problem since the client SYN retry will immediately result in a successful connection because the clients were legitimate. However, the SYN drop and SYN client-side SYN retry will cause a certain amount of delay, which is a concern. Therefore, in addition to disabling SYN cookies, it will be better to increase the size of Kafka's listen backlog so as not to cause the SYN flat condition in the first place. Unfortunately, the listen backlog size is currently hard-coded at 50, so it cannot be increased. Therefore, KIP 764 proposal is currently being proposed and discussed with the community. This is a summary. We have learned that SYN flats are possible on a large Kafka platform like ours, where many clients are connected in a platform. We also learned that on Linux kernel prior to 5.1.0, a bug in SYN cookies cannot cause a window scaling of the producer and broker to be different, resulting in a significant degradation in TCP throughput. We also learned that tcpdump, namely SSBCC, greatly help us to investigate network issues, including kernel internals. This concludes my session. Thank you very much for your attention.